I'm John Malcovitch.
And I'm Zotta. We're here at Cornell University with the SRCCS research group. We're studying physics.
So here we are at Newman Laboratory where we do most of our work. We're actually working with the Superconducting RF cavity group. So these are really interesting and very complex pieces of equipment, but we each have our projects to aid in the development.
So in a second we'll take you inside the lab and show you what we've been working on. Right here we have the pit where we test our RF cavities to see different things about them, different temperature warming and stuff like that. And what we're about to do is take it out of the pit in the ground here, so we'll see what that looks like in a second. This is what the cavity looks like when we have it on the chassis and out of the pit. Now, just briefly explain to you how this works because I know it gets confusing after a while. But basically, what we have here, the wires come down and connect to these boards that are stationed all around the cavity that's inside of here. And if we pull out one of the boards, I'll show you what we got here. We've got a board that perfectly fits around the cavity with resistors all around it. And the resistors, when they're in contact with the cavity and we have power running through it, register a voltage. And that voltage is associated with the temperature in a sense. And one cool thing about these resistors is that they're temperature sensitive. So as the temperature changes, so the voltage across them changes. So using that, we can get a complete map of what's going on in this cavity. Well, that information has to go somewhere. And so where it goes is to this computer program that we're putting together. It's based off of MATLAB. And when I got here, all the code was written mostly for understanding and collecting the data and now putting it in some sort of results. But the codes were all kind of typewritten, so you had to call the function first. So what I'm doing, what my project has been so far, has been creating a GUI to get all the functions in one place. And so we only need to push buttons on the GUI to do what we wanted to do. So here we are in the student office where we do most of our work, all the students. Well, this is mainly where I've been doing most of my work. What we have here is obviously my computer where I do a lot of programming, and what we have here is the program that I use to read the information off of the setup we showed you previously. So this is what we've come up with, and I'll show you a little bit about it. So as you can see, this looks a lot better than what we had previously with all the different codes that we had to go through. Now we have buttons. Each button has a specific function that it calls back. And previously we had to call these functions line by line, so we had to type in each function and make it do what we wanted to do. Now we just take different radio buttons or select different buttons and push different buttons and we can make beautiful things happen like this. So this is a graphical readout of all the temperature across the cavity.
Okay, so this is a single cell test cavity. And what I'm designing is a baking system that will actually fit within the test stand. Because the secret of the in situ baking is an ultra-high vacuum being maintained inside, while the outside is actually cooked at 120 degrees Celsius. So the inside will eventually reach 120 C, which is why you hold that temperature for about 48 hours. At which point there's chemistry magic that happens, there's some physical magic within the actual composition of the cavity, which will allow it to reach, which will raise its quality factor and allow higher accelerating fields before quenching. And here we are with the old baking system, which works reasonably well for results. The only problem is, as you can see, it's not the most fixed system. There's a lot of finagling, and of course, this is a hot air system blowing in forced air, and it's filling a fiberglass box. Dan, what do you think about this system?
This system is terrible because as you have to assemble it, you're messing around with all these pieces of fiberglass, you're getting all over your skin, and you're itchy for probably the next week until you can get it all washed up. So the fact that John's building a nice new system is going to make things a lot easier.
No fiberglass included. So here we actually have my mentor's RF cavity that's designed. It's actually in its test stand, and it's in a semi-clean room. These bars here, everything you see is actually part of the test stand, and this is one of the constraints for this baking system. Okay, so here we are in the drafting room, and we have so this is our CAD model of the baking system. So it needs to be a modular system. Here I've just made a quick mock-up of the tightest constraint for a baking test stand. As you see, it is in 3 sections with several different layers of insulation. Here we have our electric heating element. So this is currently in fabrication, but maybe we can show you a little bit about the control system. Okay, so here we are with the components of the baking system that we have right now. So I just literally a few minutes ago picked up the aluminum from the machine shop for the actual shell skeleton. So here we have the electronics. I designed and built this system. I did a little light fabrication of this chassis, but that's not the fun part. So what this is it's actually a PID temperature controller. And so this will read a signal from a thermocouple, which actually adjusts and sits in and will actually get the temperature of the niobium cavity, so we can keep it right at 120 degrees Celsius. This actually then feeds a proportional signal out to a silicon-controlled rectifier. So instead of just doing on-off cycling to like a solid-state relay, this actually sends proportional voltage and varies the amount of current which is let through, so you can get very precise control over what your heaters are doing. The heaters themselves are nichrome. And those are all set, and maybe we'll show you a little footage of the heaters in testing. So we've had a great time this summer with this program. We've had a lot of fun, but we've also learned quite a bit with these projects.
So we want to thank you guys for watching, and hopefully this has given you a good idea of what we talked about.